Now I'm recording. I am streaming, I am sharing my screen. I got that part. Why are we here?
Oh, that's way back.
Yeah, I'm dead serious. The short answer is this course meets a college level requirement that you need to get your degree, right? That's the practical answer. But why do you think this material is necessary?
Because we'll be able to use it when we're doing research.
Research in your disciplines of what flavor specifically? Quant. Yeah, how many of you are qualitative researchers? Okay. You had to take classes, right, to learn how to do those techniques, and then you had to do them on real data for that information to sort of start to seep in. The same is true for quantitative methods. At the very least, you would want to be able to read research that uses quantitative methods and have a sense of what they did, right? So what we're trying to do is learn ways to summarize quantitative information. So far, we've talked about summaries that are univariate, which means what? What does that word mean? Just one, like one variable at a time, right? And we're just now starting to talk about things that are bivariate, which means two variables at a time. So bivariate is about association between variables. Univariate is about the amount of the variable. It's trying to characterize a sample of information with key pieces of summaries, summary statistics, as it were. So if I have a quantitative variable, right, what are two things I'd want to know about it? To be able to convey to someone else, how are my people behaving in this index? Yeah, more generally, central tendency of some kind, of which the mean is one kind, and dispersion, of which standard deviation is another. And add to that standard error. Standard error gives us an index of imprecision of that estimate. Like if I told you the mean is 12 ounces of caffeine today, is it definitely 12 or like 12? The more people you have, the more you can say 12, absolutely, because you have a small standard error. Meaning that if you took many different cans, many different samples, the amount that you would get is going to be really similar across those samples. So let's see here. Questions from the audience. Are you sharing your screen? I thought I was. Let me stop the share and restart it just in case. Maybe there's an order of operations things I missed. Okay, I should be sharing my screen. You're looking at a blank screen. You're looking at my Windows, beach desktop thing right now. So I'm sharing a blank screen. Yeah, I kind of like beach pictures, especially in Iowa, where, there is really no such thing. We got it, okay. Yeah, back at KU, they had something called Wesco Beach, which was just a joke because it was a concrete building with like a big concrete area in front of it that people would hang out, and they called it Wesco Beach. So only in Kansas, yeah, I know. But anywho, so the things that we've been talking about so far is just describing the variables and then trying to reference them relative to some sort of expectation. Hypothesis, yeah. So when I say this should be 12, right, my expectation, what's the word that goes along with that? What kind of hypothesis?
Null.
It's null. The term null means zero, but it's not always zero. It's really just expected. So I can say, I expect that there's 12 ounces of liquid in this can. I expect that the proportion of 3-year-olds is 60% of the class. I can make these sorts of expectations. And so we're trying to learn the process of translating what we have onto that set of expectations. It's a shift in perspective. So if we did the proportion example again, since that's the one that we were talking about, what I have in this example data set is a gender breakdown of 61% male and 39% female. That's what it is. This is a relatively small sample. It's a subsample of a bigger data set that only has 100 people. So how reliable, how trustworthy do you think these proportions are on 100 people? You're trying to convey that, right? So standard error of the mean, in this case of the proportion, is one way to try and convey that. That's the average distance of the mean from the population mean across samples. It's the amount of wiggle. And roughly 2 standard errors around the mean gives us our 95% confidence interval. So we have this expectation that if we did this sampling procedure over and over and over again, the proportion of males would be somewhere between 51% and 71%. Okay, cool. Now what's it supposed to be? Well, yeah, what's the null, right? I get to decide that. I'm the researcher. I picked 50-50. Does anyone know, is that actually accurate anymore? I think there's slightly more females than males in terms of biological sex, if I'm not mistaken, but I don't know the research on that. So if I think that this proportion 0.61 should actually be 0.5, how do I answer that question? Well, now I've got to put my 0.61 back into the context of what it would look like if it were 0.5. What amount of wiggle around 0.5 is acceptable? So Z is the difference between what I have, my 0.61, what I thought it was going to be, my 0.5, divided by my standard error, and the Z value of that works out to be 2.2. So what's the scale of this thing? Because this is an index that gives us our expectation. Way out. So what's the middle of Z?
0.
0. What's the middle of T? Also 0, yes. The difference is how flat they are. And in this case, because we're not worried about estimating variance, we can use Z. T works the same way though. So yeah, the range of expected on Z is plus or minus 2 is 95% of the I would say the values that we would find. So that's expected, it's within about plus or minus 2. This is outside of 2. So we're trying to translate our data onto an expectation. If in reality the proportion is actually 0.5, with what probability, with what frequency would we find an actual population or a sample proportion of 0.61? Not very often. So this suggests that no, our sample either doesn't come from the population or the population mean is incorrect. One of the two, right? You can think about it either way. And note one-tailed versus two-tailed, these things. So the labels of these says one-sided probability greater than Z, or two-sided probability greater than the absolute value of Z, excuse me. The one-tailed is exactly half of the two-tailed. Because what these probabilities refer to is, for a two-tailed, the area under the curve to the left of minus 2.2 plus the area under the curve to the right of positive 2.2. It's both put together. Both put together is this p-value of 0.0278, like 3% of the time. You'd see a result more extreme. One-tailed is half of that because we are ignoring the possibility that the proportion could be too small. It's 0.61. There's no way that it could be less than 0.5. So if we go, okay, what if we put all the area over here? Just this half has a probability of 0.01. Just that half. So when I ask you for p-values, I'm asking you for two-sided. Willing to accept unexpected in either direction. That's what that means. So the one instance in which I could think doing something like this would answer a research question is in defense of your sample. If your sample is supposed to be from a population that has known characteristics, how well does your sample characteristics compare to that expected known? That's an instance in which you would have these techniques at your disposal. That doesn't happen very often. What's way more interesting are measures of association. So, is exercise good for you? I'm told. I haven't exercised and I don't even know how long, but I'm told it's good for me, right? How would you measure that? Well, you would want to see if people who exercise more have better health outcomes, right? Lower blood pressure, at the sort of lower mortality rates. Pick a health index, right? Associations between variables. That's the second part of this that we started talking about. And so when we get to correlation, that's one kind. What are correlations for? What do they tell you about? Relationships. Associations. I would accept either of those words. Yes. So let's say association between what, and what kind of association? For what kind of variables would a correlation be an index of association? Pearson is the type of correlation we're talking about, but when I said numbers, that's what I'm looking for. Numbers. So
keep saying stuff.
that's fine. I like saying stuff. I appreciate that. I really do. But numbers, otherwise known as quantitative variables, right? When the numbers are numbers. So if I have blood pressure, right, that's a number. Number of times I dragged myself to the gym, right, that's a number. Or maybe I just walked in and swiped my ID, as most of the faculty do, because you get a discount if you go 4 times in a month. And so there are literally people that are like, beep, thanks, I'll take my discount. I'm gonna go home and eat some potato chips now. But yes, numbers. So a correlation is an index more generally of an association between 2 quantitative variables. The specific flavor of that we have is Pearson. Pearson is a linear association between 2 variables. If people are higher than others on X, are they higher than others on Y? If so, that would be a positive Pearson's correlation. If you're higher on X means you are lower on Y, that's a negative association. And the nice thing about Pearson's correlation is that it's on a scale that is readily interpretable. That's why we have it that way. So if I have a correlation of 0, what does that mean?
None.
No association, right? If I have a correlation of 1.
Perfect positive.
Perfect positive, lockstep. If I'm higher on X, I'm higher on Y. Correlation of -1.
Perfect negative.
Perfect negative. So anywhere between -1 and 1 is your index of association. So in the example that we looked at, we had, for instance, a correlation of 0.45 between family income and education. So people who have more education have more family income, 0.45. So this p-value that's underneath it is asking, how likely is it, what proportion of the time would we see a correlation of 0.45 if what were true? What is it comparing against? What's our expectation?
Education to family income.
Those are the pair of variables.
Okay.
But what does this p-value refer to? Yeah, this is actually the label that goes with education. So this is a correlation. This is a p-value that refers back to that correlation. It's trying to tell you about how expected versus unexpected it is. But what is expected? What's our null hypothesis here that this is testing for us?
0, no difference, right?
0, no difference. That's specifically what our expectation is, against 0. So if the correlation were really 0, with what probability, what proportion of the time, would we see a correlation of 0.45? Not very likely. Yeah, really not likely. So what it's hiding from you is the intermediate step that got this p-value, which is your t. So R and sample size together make up your t-value. There's a formula in there. But more people means it's easier to say that a correlation is unexpected, different than 0. That's referred to as power. We'll talk about that later today too. So this is one kind of association. It's linear. If these 2 variables don't have a linear relationship, Pearson's correlation will not pick that up. If more education doesn't matter after some point, like if it's good if you graduate high school, it's better if you graduate college, but getting a bachelor or a master's, PhD, JD, whatever, if there's diminishing returns, that sort of idea of a curve leveling off, Pearson's correlation won't pick that up. Do you want to know how to pick that up? Come back. Keep coming back to class. We're going to do that. It's a cliffhanger. You need a model. You need a way to phrase that sort of pattern as a testable hypothesis. And we need models to do that. We're going to get there, I promise. Yeah. So one kind of correlation is Pearson's. For quantitative variables, it's a linear relationship. The other old white guy correlation, do you remember that one? Spearman, yes. What makes Spearman different than Pearson? Do you remember that? Rank order. Rank order. Spearman's correlation first converts the numbers, the two variables you're trying to correlate, into their rank order. So the highest one is number 1, second highest is 2, third highest is 3, etc. It then correlates those rank orders. Now, why would you do this? 2 instances. One is if you're worried about outliers, you're worried about extreme quantitative variable values that would have undue influence on the solution. So we looked at a picture. Let me find Anscombe's quartet. Where's that picture? It's coming. This one. This is slide 31. Blow this up a little bit. This picture right here. If I didn't have that guy, what would my correlation be? Well, X is 8 for everybody. X is a constant. So I'd have no correlation whatsoever if it weren't for that guy. So if you're worried about that guy in your data set, you're uncomfortable with the fact that one person has so much control over the thing that's supposed to describe your entire sample. If I did Spearman, I would have all of these people would be a value of 2 in the rank order, and this guy would be a 1. He is highest on X, next highest are these guys. So instead of having 18 versus 8, it would be 1 versus 2. So now this 18 doesn't matter as much. You've reduced his influence. The other situation in which Spearman would be useful is if you're not actually talking about numbers. There are a ton of variables like this in the social sciences that are ordinal. How likely is it that Lisa's going to the gym today? Not very likely, somewhat likely, very likely, right? I could call those 1, 2, 3. I could call those -12, 0, and 5,000. Both of those are correct because these are not amounts, right? These are labels. We can all agree that more likely is more than somewhat likely, but we can't agree on what the numbers go with them. So that type of variable that's ordinal, you may as well just have a rank order, right? The strongest, most, very likely is 1. Somewhat likely is 2. Not very likely is 3. Because the numbers don't really mean anything. So ordinal variable associations, Spearman is designed for that as well, such as what we were looking at last time, whether money and friendship are related to happiness. So I have a variable of income here that's an actual number. It's income in log $1,000. I have how frequently you socialize with your friends on a scale of 1 to 7, where these are just labels, right? They're not real numbers. But you can say that 1, whatever response goes with that is the highest or the lowest. 7, whatever answer goes with that is the highest. And the same thing with happy here. This was supposed to be a 7-point scale, but no one agreed that they were unhappy, so it goes from 3 to 7. So there's a correlation, a Spearman correlation. Let me find that one. Right here. 0.11 between how often you socialize with your friends and how happy you are. So is that positive, negative, or somewhere close to 0? Make this easy. Somewhere close to 0, right? It's a correlation of 0.11. So it's itsy bitsy positive, but mostly 0. So if the true correlation were 0, how often would we see a correlation more extreme than this? Like 39% of the time. So the area that is to the left from a correlation of minus 0.1 plus the area that is to the right of a correlation greater than 0.1, that area is 39%. So in terms of decision making, we'd say, no, we don't have enough evidence to say that this is different than 0. This falls within expected fluctuation. So we would do not reject the null or retain, or if you're writing this up for publication, this is a non-significant positive correlation. You would give the correlation value, you would give the corresponding p-value, and you would interpret it such as I have right here. Where is it? Yep. Happiness was not significantly related to family income. That's this correlation next door, nor to frequency of evenings with friends. And what's this thing right here? It's related to sample size. It's actually sample size minus 2, otherwise known as degrees of freedom, denominator degrees of freedom. Because there were 73 people who answered both questions to be able to examine an association. All right, and then here is my pretty picture. So histograms on the diagonal, scatter plots on the off diagonal for those. And in Stata, the command is Spearman to get a Spearman correlation. You have to ask for p-values that go with them, as well as the sample size. All right, how are we doing? Questions or things you'd like to hear again, or things you'd like to hear differently? So what about the other kind of variable? Besides numbers, what's another kind of variable? Categories, yeah. Like, what's your favorite kind of pet? What's your favorite kind of ice cream? Where are you sending your child to kindergarten next year? Public school, Montessori, or other private school? Just hypothetically, right? Not that I'm dealing with these issues right now. That's my other class's homework. They're predicting that kind of outcome. But yeah, some variables are not numeric. They can't be. So how do we examine associations for those kinds of variables instead? If we don't have anything even remotely resembling a number, right? If the categories are labels and we wouldn't necessarily be able to agree on their ordering, then what? None of these things will work. We need something new. So I'm gonna skip a few things and then come back to it in the interest of keeping you guys working on your homework, because this is the last measure of association that we need to talk about. This is slide 37 in lecture 2. Bivariate association for categorical variables. So this is an example from your textbook that I borrowed. It's archival data related to whether or not someone was sentenced to death for committing a crime as a function of their race, which they have dichotomized into white versus non-white. So the question is race related to propensity to get a death sentence? So these things are binary. They're not really numbers. It's an either-or proposition the way that this was measured. So this process of trying to figure out how many people are in each unique combination of groupings is called a cross-tabulation. You already know how to do this. The syntax for it is available in Proc Freak, so you don't even have to learn a new procedure. So the language that goes along with this table, the unique combination of values across variables is called a cell. So for instance, there are 33 non-white people who were sentenced to death. There were 33 white people who were sentenced to death, 251 non-white people who were not sentenced to death, and 508 white people that were not sentenced to death. Those are the numbers. That's what you get when you put it together. Now, how do we use those numbers to answer the question? If we just eyeball it, what do you think? You think race is related to propensity to get a death sentence based on these numbers? Yeah, I don't need stats to tell me this, right? Like, it's like, among the people sentenced to death, it's half and half. Among the people who were not sentenced to death, there's like twice as many white people. That looks significant to me, right? But I need some stats to back that up, because I can't just wave my hands at the numbers and expect to get published. Or to graduate, for that matter. So we have to find some way of establishing, well, if there were no association, what would these figures look like instead? So it's the analog to, if there were no correlation, we expect a correlation of 0. If there were no association, what's the analog to like expected here? And the numbers that are in parentheses are the expected cell counts. That's the baseline if there really was no relationship here. Where those numbers came from is this formula right here. It's the number of people in the row. So for instance, if I'm trying to recreate this 22 right here, I have 284 people in this row of non-white people. I have 66 people in this column of people who got the death sentence. If I divide by the total number of people that I'm talking about here, which is 825 right here, I get an expected count of 22 people in this cell. So there's actually 33. Based on just the proportion of white people and the proportion of people who got a death sentence, that cell would be about 23 people if these things were unrelated. So there are more non-white people who were sentenced to death than expected. Expected is 22 versus 33. Analogously, if these things were proportional, if there was no association, there would be an expected 43 white people who were sentenced to death based on the number of white people and based on the number of people with a death sentence. Instead, there's only 33. So it looks like non-white people are relatively more likely to get a death sentence, whereas white people are less likely. That's the direction of the pattern. Now, is it significant? Is that pattern unlikely to have occurred by chance? We got to do a test, exactly. I got to get a p-value. I got to get some sort of indication here. Welcome to your new friend, chi-square. So this is the Greek letter chi, C-H-I, square. It looks like an x, but it's not an x. Because x is a variable. X is going to be what we use for predictors. So this is chi-square. This is a summary of all of the discrepancies for what you actually got versus what you were expected to get if there is no association. So it is the observed number of people in each cell minus the expected number in each cell squared. Can you guess why we're squaring it?
positive.
To keep it positive, because under expected and over expected both matter. And then we divide by the number that are expected. So if we do this for each cell, the math is right here in this box. Here's this cell right here, the yes non-white. Here's the cell next door, the no non-white, and so forth. That sums to 7.71. Okay, what the hell is that? Is that good? Is that a lot? Blech. Well, it's relative to a distribution, the chi-square distribution. There is 1 degree of freedom here. So this is a different kind of degree of freedom than you know already. This is your first instance of what is known as numerator. Because what we know in here, if I know the margins, I know how many non-white people were in the data set. I know how many white people. I know how many people got the death sentence, and I know how many people didn't. All I have to know to figure out all 4 of these cells is how many people fell into one of them. I can work it out from there. I know that if I have 508 white people without a death sentence, based on 541 total, I know there have to be 33 over here. And if I know that, I know how many are in the other cells. So I only have to know one thing to fill out the whole table. That's numerator degrees of freedom. How many things do I have to know to be able to finish this problem? In the chi-square distribution, you have the expected value is the number of degrees of freedom. So if there were no association on 1 degree of freedom, I'd have a chi-square around 1. My chi-square is 7.7. That's a lot more than 1. So you can compare where chi-square falls on a distribution and get the exact p-value that goes with it. So it works out that the cut point for what is unexpected for chi-square, if you have 1 degree of freedom, is 3.84. 7.7 is more than that, so yeah, it's significantly unexpected. There is an association here. Now the thing about chi-square that's different than the other ones that you know in terms of distributions is that it's only positive. It's in squared units because everything is positive. So we don't have to worry about the left side versus the right side. It's all right side. So if we feed this into software that gives us p-values, we would see a chi-square this big, 7.71, 0.005% of the time, 0.5% of the time, if there were no association in the population. So it is really unlikely that we would see this degree of discrepancy from what was observed versus expected if there was no pattern of association here. So chi-square is the test statistic directly. It's like your t or your z. It's the thing that gives you the probability of how unexpected this is. The next step then is to try and quantify, or to figure out what is the pattern here. Because all we know is that race and death sentence are associated. That's not the end of the story, right? We need something that's analogous to the correlation direction, right? Question?
Where's the null hypothesis?
The null hypothesis is that there is no association, and unlike that being one number, it depends on the number of degrees of freedom. So in chi-square for 1 degree of freedom, a chi-square that would be no relationship would be 1.
Okay. So because it's 3.84 and not 1, we're rejecting?
3.84 is the critical value for where you would not see a chi-square that big more than 5% of the time. So the, let me see if I can pull up.
Is there like a table or something?
There's a table and there's a picture. It'll be faster to ask the Google. Wiki, chi-square distribution. I know I have it somewhere in my slides, but I didn't put it in this one for whatever reason. Here it is. Let's look at this picture. Thank you, Wikipedia. This is a chi-square distribution under different degrees of freedom. We're the yellow one. Okay. So what we just found is out here between 7 and 8.
Oh, I thought it was 3.8.
3.84 is the cut point for where the area changes to be less than 0.05. So in this case, it's not two-sided.
Oh, so that's more in reference to the actual slope.
3.84 is right here.
Uh-huh.
This is the point where you would expect a chi-square bigger than this, less than 5% of the time.
I see.
That's the dividing line between
it's kind
significant
of
and
like, on this one, it's kind of like that part.
draw again for me.
So if we're looking at a slope like this, it would be like the part that's kind of not really anything going on.
Yeah, so if you
It's kind of like that.
if you take z, right, that has the two sides, and you fold it in half,
Right.
that's this. Z squared is chi-squared.
Oh.
Yeah, it's a squared metric instead of an original one, but it's the same idea. There's only one side where this thing.
3.84 is the moment where it just stops becoming relevant.
3.84 is the moment where the probability of observing that result is less than 0.5. 3.84 is the dividing line between significant or not, expected or unexpected.
So kind of like outside of the confidence interval?
Yes.
But just on a different,
Metric.
yeah.
Yep.
And then in this case, we're looking at the k equals 1.
We're the yellow line. We are out here. So really, really unlikely to get a chi-square of 7.71 if there's really no association.
So back to my first question, so the null hypothesis is in reference to wherever k is?
Yes.
And then in this case, k equals 1 puts the null at 1?
Yes.
Okay.
Yep. Exactly. Yeah, it's sort of a sliding scale in terms of what it should be. The thing is that chi-square doesn't tell you the strength of association directly in a metric that you know what that means. Like if I tell you I have a correlation of 1, you know what that means. If I tell you I have a chi-square of 7, you'd be like, okay, is that good? Well, what's it relative to?
Right.
Is it relative to 1? Is it relative to 2? And so it's not as intuitive of a metric. It's just a test statistic.
Okay.
We still need to do the work of translating a chi-square of 7.71 into some sort of measure of association that has a range where we know what to do with, that's standardized. We haven't done that part yet. Yep. Yeah, thank you. So the pattern then, the way that we would determine the pattern, homework question, is to look at the differences between the expected and unexpected. The pattern here, if I just focus on, say, one cell among columns, I have it written down here, among non-white defendants. So if I go over here, for this right here, 33 versus 251, there is a greater proportion of non-white defendants given the death sentence than expected. I expected, if based on just the frequency of each type of person in my data set, that 22 people would be given the death sentence. If it were completely fair and had nothing to do with race. I got 33 instead. So yeah, there is an association. Being non-white makes you more likely to be given a death sentence. And I'm phrasing it that way because they were non-white to begin with, and then something happened and they got put on trial. I could say, I guess in theory, being given a death sentence makes you more likely to be non-white, but that sounds weird to me. These are associations, point being, that's not causal, but one of these things clearly came first in terms of life. So I'm asking you to do a cross-tabulation in your homework of number of children in each classroom who are 3 versus 4 years old. And it's the same sort of idea. What is the pattern? Significantly associated is not the end of the story. It's how are they associated? And we can't talk about positive or negative in the same way as we can with numbers because these aren't numbers. But you can phrase it as more people in this category than you would expect, or less people, fewer people in this category than you would expect. So the problems that Dre, you were just saying, like how do I know what to do with this, what's the null? Here's an example of that same problem. Here's a cross-tabulation among a variable that has 4 categories, which is number of child abuse categories checked in some sort of checklist, versus whether or not they were abused as an adult. Now I can tabulate the number of people in each of these child abuse categories and the number of people abused as an adult. But now I need more than one cell to figure out the rest of the table. I actually need 3 cells. I need to know three of these 8 cells, and then I can work backwards to figure out the rest. So I need to know 3 things to solve this problem. So my sort of default null hypothesis chi-square now is 3. If I do the same math, the difference between what was observed for each cell minus what was expected in parentheses, square that, divide by expected, sum across all 8 cells, I end up with the chi-square of about 30. Is that good? I don't know. Let me go back to Wikipedia. Now we're on the teal line, k equals 3. This one, we're out here at 30. So yeah, I can make a guess that, yeah, 30 is really unexpected. There is a pattern. These things are not unrelated. They're related somehow. How? So yeah, the p-value that goes with the chi-square of 30 on 3 degrees of freedom is 0 to like 6 decimal places. Yeah.
Are these calculations that we are doing?
No! The software is going to do them for you. Always. It's better and faster at it.
So, I guess there's lots of time before homework 2 is done, but at some point, will we have that opportunity to walk through that?
Yes.
I don't mean to like take the lecture off course.
No, that's actually where I was heading next. I swear. That's where I was going. Because like the next logical step is, okay, you show me how do I do this in life, right? And the answer is never get out your calculator. Like that's for pedagogy. I'm filling in the numbers just so you can see where they came from. But the point that I wanted to make here is like the conclusion is, okay, these are associated. Now what? Where are they associated? Right? There's a potential for an association among every combination of 2 by 2 tables in here. I just know there is an association. I have no means to describe it. That's where chi-square starts to fall apart in terms of being useful to describe relationships. And these sorts of relationships are better handled in models as well. So I'm teaching a class on generalized linear models right now, where they're learning how to predict these sorts of categorical outcomes from other categorical predictors or quantitative predictors. Now, how do we do this? The question.
What's the name of the course that you'll be teaching next week?
If it comes back next spring, it may come back in 2 years, I'm not sure, but it's the one I'm teaching right now. It's Applied Generalized Linear Models. It's a brand new course. It's how to predict something that's not a normally distributed quantitative variable, because everything else is not that. But to your points, how do we do these cross tabulations and get the chi-squares to spit out? It is a procedure that you already know. It's called proc-freq in SAS. You already know that one, yep. And in Stata, it's tabulate. The part that is different is right here. Can you see that? That's an asterisk. You can request cross tabulations of pairs or triads of variables by listing the 2 variables with an asterisk between them.
So they're using the asterisks in more than one place because it was just for comments. Now if it's in the middle of the code, it means something different?
Yes.
Yay.
So say what you said again.
So
What page are you on?
I'm on
12.
page 12, example 2, thank you. If I put an asterisk here in SAS, that is asking for a combination summary of these 2 variables, a cross tabulation. So you guys have done this so far without the asterisk, and if that happens, you would get one table that would have the first variable, and another table that has the second, but they're not in relation to each other. If you want them in relation to each other, such as age group by classroom, for example, then you need the asterisk. And so then we end up with a table that looks like this, where I have one of the variables here, this is whether or not females are suited for politics. So it's phrased as not suited, and if you say yes, they're not suited, that means women are not suited for politics. Yes. No means no, they are not suited for politics. I know. I didn't make this up. This is a terribly worded variable. And then the other variable I picked was whether or not they're married. So the other things that I'm asking for here, I'm suppressing some of the output that's going to clutter up my screen. I don't want row summaries or column summaries at this point. I'm going to set an alpha level of 0.05 for my hypothesis test. Can you guess what CHISQ stands for? Chi-square. These two we haven't talked about yet. These are effect sizes. And the very last thing, the word expected, that's what gives you how many people should be in each combination if there were no association. The expected cell counts.
Null hypothesis.
If there were no association as the null.
Okay.
Yep. So there were 18 people who said, no, women are not suited for politics, meaning they are suited, who are not married. There were 31 people who were married and agreed with that. The second row is the expected cell count. So the 20 relative to the 18. There were fewer people in reality, the 18, than were expected based on how many people answered no to the question and how many people are not married. So note the expected cell counts in this case have decimals. 20.5 people were expected. It's a little weird, but the math makes it that way. So more people were expected than were present in this cell. Likewise, if I go down here, people who were unmarried, who said, yes, women should not be in politics, there were 10 people who said that, and there were 7 people who were supposed to be in that cell, the expected cell counts. So if I eyeball these things, it looks like there are more people who are unmarried, can I say Neanderthals? Can I say that? Than would be expected. So there may be an association between there. But I'm not going to just eyeball it. I'm going to go down here to my happy little table.
Is the frequency missing? Does that mean that they just didn't answer the question?
That means there were 33 people who did not answer one of the questions, and so we can't include them in the cross-tabulation. So there were 100 people in the data set. 33 people are not part of this analysis. Good catch. Here's my chi-square. 1 degree of freedom, meaning I only have to know one of these combinations of cells to figure out the other 3. It's number of rows times number of columns. That's how you know that. The observed minus expected squared over expected, if you add up all 4 cells, that chi-square value works out to be 1.9. I would see a chi-square that extreme about 17% of the time if there were no association. In other words, this falls into expected fluctuation. The tendency that it looks like is there for there to be more Neanderthals who are unmarried, I'm going to stick with that definition, that tendency does not cross the line into unexpected. Non-significant. The association appears to be non-significant. We don't have enough evidence to say there is this pattern there. The deviations of what actually happened, like the 18, from what should have happened if there were no association, are not strong enough. They could just be due to random noise. All of these other things you can ignore for this class. Statisticians have fought for like hundreds of years as to the right version of the chi-square, and these are all someone's adjustments that they got published doing something else. They're all variations on the same thing. One thing, though, that you do want to have is this thing right here. We talked about this briefly last time. Phi, or phi. I've heard it pronounced both ways. That's another Greek letter. That coefficient. Do you know what that is? It is the same thing as a Pearson correlation. Phi is just the name for the computational shortcut that you can use if your variables are binary instead of quantitative. It's the same damn thing. If you were to run proccore on these two binary variables, that is the number that it would spit out. Did you have a question, Dre? Did I see your hand?
Yeah, if you, when, a few steps ago,
Okay.
you said that unmarried 20.5 is not significant enough, and I was wondering, is that because of how far it is from 26.87?
So 26.87 is just the frequency. That's not part of that's our percentage. It's converting the raw numbers into percent out of 100. That's not part of our test. So what I was talking about is comparing like this 18 with this 20.5. I can't highlight just one of them apparently, but this is where I am. So the reason that this result, this association is not significant, meaning that I'm saying there's no association between these variables, is twofold. Number one is just the raw size of the difference here, right? There's 18 people and I thought there was going to be about 20. That's pretty damn close. So
it's because it's so close.
It's because it's so close and because we only have 67 people
Total.
answering these questions.
Okay, got it.
If I had 67,000 people,
Sure.
a difference that small would be notable because you have a lot of precision and power that's afforded when you have that much information to work with.
Okay. Yeah,
So-
I just wanted to make sure I knew what, yeah, thank you.
Yes. So yeah, it's the non-significance is both a function of that 18 is not that different from 20, but it's really not different when you look at how many people we have all together. It's both of those at the same time. Sample size and effect size is foreshadowing those terms. So this thing right here, this phi thing, this is an effect size. Effect size is a generic term that means a measure of association on a scale that you know immediately what to do with. A correlation is an effect size. Pearson is one flavor of correlation. But if I tell you that I have a correlation between these two binary variables of minus 0.17, now that number you know what to do with, right? It's a negative association. So that's a little tricky when you think about how these variables are categories. But it means that there's more, in this case, that the tendency to be a 0 in the no is related to the tendency to be married, the 1. So you'll see this as an example in your of age group versus classroom. It's all about the breakdown of what is more expected here. But the tendency to be a 0 on one variable is related to the tendency to be a 1 on the other variable if there is a negative association. So when we phrase it as a phi coefficient here, as a Pearson correlation, that number is pretty close to 0. So that's an effect size that we know what to do with. What would it be if it were a stronger association? What if it was really the case that Neanderthals were more likely to not be married? Yeah, negative 0.9, yeah. In this case, if it's negative association, something much closer to minus 1. And then here's a whole bunch of other p-values that you can ignore for right now. Again, that is for another class that in these models on more detail.
Isn't one of those for the homework?
The one that's for the homework is right here. Just your regular flavor chi-square.
Question 21.
Quite possibly. Let me see. Question 21. Yeah. Yeah, actually. So I'll give you a hint on these last questions here. What we've just done is figure out how to get the expected frequencies, the chi-square test statistic that goes with them, the p-value that goes with that, the Pearson correlation that goes with that, and then I'm asking for the p-value for the Pearson R. That's sort of a trick. Because if this chi-square test statistic goes with this Pearson effect size, they have the same p-value. So reinforcing that as a concept.
So what would be the stata for,
The stata analog for these commands? Let's look at those.
you said it was question 17 to 21, right?
What we did today was actually 14 through 21. How to get the expected frequencies, the chi-square that goes with the difference between expected and observed, and the effect sizes and p-values that go with that. In Stata, the code is similar but not the same. We have tabulate without a star. If you list two of them on tabulate at the same time, it assumes you want a cross tabulation. Cell means give me the number of people per combination, per cell. Tab 2 is how you get the additional output related to the significance test, chi-square, and expected frequencies. And the other effect sizes that we haven't talked about yet are the third line, odds ratios and risk ratios. So I will warn you, in Stata output, I discovered this last semester and I've still not found a way to rectify the situation. Stata spits out two tables. The first table contains the frequency, like here's my 18, and the percentage. So 18 people is 26% of the sample. The next table down here repeats the frequency, so here's my 18 again, and here's my expected frequencies. Stata gives expected frequencies to 1 decimal place, and the homework system wants 2. So if you're using Stata, you'll have to do the math, unfortunately, with a calculator. But the good news is that the math is pretty straightforward. It's right here. Number in the row times number in the column divided by total. If there is a way to ask Stata how to spit out more decimal places here, I couldn't find it. If any of you know or find it through the Google, please let me know so I can solve this problem. Because it really bothers me to have to calculate things by hand. That is unacceptable to me, but I haven't found a way around it yet.
So will we have to use that formula during the homework question?
Yep,
to get
Just show them?
to get the second digit that goes here, because the homework is correcting it to 2 digits. That's the problem. Or you could just cheat. You could enter everything from 0.45 all the way up to 0.54 and see what takes. That works too. If you don't have a calculator, yes, that's being inventive. I like it. But SAS gives you two places, so that's where the homework system is built in SAS. Here is Pearson chi-square for 1 degree of freedom. That's your chi-square value and the corresponding p-value, and that matches SAS exactly. And I think we have now hit everything on the homework. Let me check. So I didn't ask for, yeah. I didn't ask for any of the effect sizes for chi-square, so that's good that we skipped those. Yeah. Questions? Yes.
Sorry, back to number 21.
Number 21.
You said that number is the same as something else, and I missed what you said that number is the same as.
So there's 3 pieces of information that you need to answer 4 questions, meaning one of them is redundant. The chi-square gives you the place on the continuum of where unexpected versus expected lies, right? That's your test statistic. The p-value then comes from that distribution. So, for instance, in this handout, I've got a chi-square of 1.9. The probability that I would see a chi-square of 1.9 on 1 degree of freedom is 0.17. So that's the dividing line. The effect size that goes with this, because I can't look at this chi-square and know intuitively what the hell it means. I have to reference it back to degrees of freedom, and I have to have like the distribution memorized in my head. The effect size that goes with it is the Pearson correlation, which is labeled as phi, or you can ask for it directly using PW core and Stata. So this is a way of translating this arbitrary test statistic into a metric that we know what to do with. But the significance of that effect is the same. These are two different scales, essentially, of saying the same thing. So if the p-value for the chi-square is significant, then the p-value for this correlation should be exactly the same. Because they're
Your
referring.
homework said that that was wrong.
It said that that was wrong.
And so I put in a number from the next table and it said it was right.
Said it was right. Which number did you put in?
The two-sided, not just right above that, the Fisher's exact stuff.
Fisher's
I put
exact.
in the two-sided PR, the last one.
This one?
Yeah.
Yeah.
And that's what it said was correct.
It could be correct to 2 decimal places because a lot of these p-values are going to be the same. I'd have to look at it to make sure because I didn't ask anything about exact tests inside the homework system. So it might be a coincidence that that p-value was right. But it should be the same information in terms of what the p-value is from a correlation versus for the chi-square. Take that back. Denominator degrees of freedom, that's the difference. It's going to be very close, but not exactly the same because correlation is used to t, whereas chi-square doesn't have denominator degrees of freedom. So I'm going to walk that back. It will be very close, but not exactly the same number.
Okay.
Because it's relative to a different
And
reference.
those two numbers that I have are very close,
Mm-hmm.
but they're like 0.01 and some change off.
Mm-hmm. Yeah, the test statistic for chi-square is agnostic to how many people you have. There's nothing in it that has sample size, whereas the test statistic t for a correlation has sample size in it, and that's the difference that I forgot about in this class, because in the class that I starts in 15 minutes, that's not a thing anymore. So I apologize, I jumped the gun in terms of what I said. The p-values will be very close, but to the extent that you don't have a lot of people, this p-value will be bigger because it takes that into account. All right, I'm rambling. I think that means it's time to go.
So, quick clarity.
Quick clarity.
The formula that you were just talking about a while ago, when we were talking about Stego,
Mm-hmm.
are you talking about formula on slide 39?
37.
Because,
It's right here. How to get the expected cell count.
thank you.
Mm-hmm. All right. Office hours start today around, I'll be here 3:15 to 4:30. I think I have some Zoomers in there, so if you come, you may have to wait a few minutes if you come right at the beginning of those. Otherwise, let me know if you have questions via email. See you all later.